I'm going to do a switch share. Okay, there we go. Okay, this says, this is kind of a review of what we were doing in other chapters. Identify the hybridization and the bond angles for the following. Carbon bonded via 4 single bonds to adjacent atoms. So for A,
Read that at all.
oh,
I can look in my book though.
how's that?
Much better.
So what's the hybridization here?
SP3.
Angles?
1095.
Okay, how about B? Carbon via 2 single bonds and 1 pi bond. It should actually be 1 double bond.
So is it linear or trigonal planar?
They're not asking for that.
I know, but
So here's 2 single bonds and 1 double bond. What's the
then,
hybridization?
SP2 120.
Okay. Okay, now that you said the bond angles, it's pretty clear that it's trigonal planar, right?
Yeah.
C, carbon bonded to adjacent atoms via 1 single bond and 1 triple bond.
SP 180.
And D, carbon bonded to adjacent atoms via 2 double bonds.
So same.
What's that?
So the same.
Same as which one?
SP 180.
Okay.
Not when you draw it like that though.
Huh?
Not when you draw it like that though.
Well, I drew it like that just to try to fake you out.
I know. Not cool.
So it did kind of fake you out. That's not good. You shouldn't be faked out by something like that.
I wasn't. I was just noticing you drew it incorrectly, Tony.
Okay. Compounds with the same attachments of atoms but different orientation in space are called which?
Would it be optical?
It would not be structural
All right.
because this is a different attachment of atoms. Now, cis trans is the same attachment but different orientation.
So it's stereoisomers.
Stereoisomers, because stereoisomers, there are 2 types. What are they?
Geometric.
And
Oh, I don't know. Is it constitutional?
optical, right? I think it's optical.
Okay. I
So
don't know.
geometric are cis trans. And optical are ones with four different things attached to a carbon.
Okay. But okay.
So when you have a carbon like this with an A attached, a B attached, a C attached, and a D attached, where A does not equal C, does not equal B, does not equal D. Whoops, not equal. Okay. Determine how many non-cyclic structural isomers and geometric isomers are possible for compounds having the formula C4H8. So we're going to start with structural isomers. And non-cyclic means that they can't contain a ring. So non-cyclic means no rings, like that.
Okay.
So let's talk about this drawing here. When you see a drawing like this, every line is a bond.
Mhm.
If you see two lines, it's a double bond. If you see three lines, it's a triple bond. If
Okay.
you see an element in there, the bonds go to that element. If you don't see an element there, the bonds go to carbon.
Right.
Every carbon must have 4 bonds. So you add hydrogens to each carbon. Each hydrogen is singly bonded, and you add as many hydrogens as you need to get to 4. 4
Okay.
bonds for carbon, not 4 hydrogens. So that's the interpretation of a line drawing. Lines are bonds. They're bonds to carbon unless another element is shown. And you add singly bonded hydrogens to each carbon to get 4 bonds per carbon. So that's how you interpret line drawings. It's that easy. Lines are bonds. The bonds are to carbon unless another element is shown. Add singly bonded hydrogens to each carbon to get 4 bonds per carbon. Okay, so back to this problem, number 8. Non-cyclic structural isomers. So if we draw this, can you see how this is C4?
Yeah.
And how many hydrogens are here? Well, there's 3 there because I only see 1 bond to that carbon.
Mhm.
There's 3 on this end.
Mhm.
That's 6 total, right?
Yeah.
How many hydrogens are bonded to this carbon here?
2.
2. So now we're at all of a sudden 8, right?
Right.
And how many bonded to this one?
2.
So that's 10. And that's not going to work for our C4H8.
Right.
So what's another way to get rid of 2 hydrogens but not add other elements or make a ring? Because if you look at this, this is C4H8, but we're not allowed to do circles.
So could we do a carbon going off of another carbon?
Well, we are doing that.
Yeah.
What you have to do is put a double bond in there.
Okay.
So this is C4H8. And so do you see the double bond there?
Yeah.
This is a different C4H8.
Right.
And this is the same as that one.
Okay.
I made that double bond a little too thin. I'm going to try and thicken it up here.
So it's the same because it's just a mirror image, it's just flipped.
Pretty much. With these are not resonance structures because you can actually pick them up, twist them around, and see if they match.
Okay.
Okay, so we only have 2 so far. But whenever you have a double bond, you have to worry about cis-trans. So for cis-trans and double bonds, you are required the following: 2 hydrogens bonded to the carbon-carbon double bond. Not 3, not 4, 2.
Okay.
The hydrogens have to be bonded 1 per carbon. So 1 to the carbon on the left, 1 to the carbon on the right. Not both on the same carbon. And if you have that, if the hydrogens are opposite, it's trans. And if the hydrogens are on the same side, it's cis. Can this guy be cis trans? Well, look at this carbon on the end. How many hydrogens are bonded to it?
2.
2. So it can't be cis trans. Can this guy be cis trans?
The middle? Yeah.
Yeah, this guy.
Yeah.
It can. Is this one the cis or is it the trans?
Well, wait, what did you point to?
The one in the middle, is it cis or trans?
I don't know.
Well, let's take a look at it.
It-
Okay, so let's fill it in.
I
Carbon, 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 carbon,
Yeah.
right?
Oh, okay, yeah.
What else is bonded to this carbon?
Hydrogen.
And since it has 3 pairs, isn't it trigonal planar?
Yeah.
Does that look trigonal planar?
Yeah.
Okay, same for this guy, right?
Yeah.
Does that look trigonal planar?
Mm-hmm.
Is that one cis or trans?
Trans.
Trans. So how do we draw the cis? Well, we draw the double bond in the same place. Okay. And here, if I do this, then I do that. There's the cis. So these are geometric isomers. So far we have 1, 2, 3 non-cyclic structural isomers and geometric isomers. But we may not be done because there's this.
Mm-hmm.
So is this a structural isomer of these guys?
Yeah.
Absolutely. Okay. Does this have, is this one a cis trans double bond? Is that possible on this guy? No, it's not. So these are the 4 possibilities.
Okay, so we have 2 of the structural.
No, these are all structural.
Yeah.
I guess, well, we have, depends on how you look at it.
Mm-hmm.
These are all, these 3, I guess you could call structural isomers, and these 2 are geometric. Or you could call these 3 structural and these 2 geometric. It's kind of a fuzzy area when you say how many structurals and how many geometrics you have. They're really all structural isomers when you compare this to the rest. And these 2 are, actually, I'm going to say they're all, well, again, these 3 are structural isomers. These 3 are structural isomers. So, and these 2 are geometric. So it's kind of hard to call them all structural or all geometric when that's not the case. So what we'll say is they're all isomers.
Right.
These 2 are geometric. And when you compare any other 2, they're structural.
Okay.
So probably the best thing to do is when you're thinking about structural isomers and geometric is think about pairs. Here's a pair. Is it structural or geometric? So how about this pair?
Structural.
How about this pair?
Geometric.
Yep. How about this pair?
Structural.
Yep. How about this pair?
Structural.
That's right.
Okay.
That's it.
I see. I think.
Okay. Are any of them chiral? So for them to be chiral, you have to have 4 different things attached to a carbon. Let's look at all of the possibilities we had again. Here's one of them. Here's another. Here's another.
I don't think they're going to be.
So these are the 4. We're looking for a carbon with 4 different things attached. So when we fill these in, this is what it looks like. Okay, so I want to do this for one of these so we can see exactly what we're looking for.
Okay.
You see this carbon has 2 hydrogens and a carbon attached. It doesn't even have 4 things attached. It only has 3. It's out of the game. So anytime you have a carbon with a double bond in it, it's not chiral,
Okay.
period.
There's just not enough variety.
You have to have 4 things attached. And they have to be different. Do you see that this has a hydrogen and a hydrogen? They're identical.
Mhm.
So it has 4 things attached, but not 4 different things.
Right.
And this one also. So when you start to play this game, you quickly find out that none of these are chiral carbons. However, if I drew something like this, that would be a chiral carbon. Because the 4 things attached to it are a CH3 at the top,
Mhm.
a CH2, CH3 at the right, a CH double bond, CH, CH3 at the left. And also what you don't see is the hydrogen because that's implied. So can you see that there's 1, 2, 3, 4 different pieces attached to the carbon?
Yeah.
So we're not talking about 4 different types of elements. We're talking about 4 different pieces. Okay. So that's number 8. What is the molecular formula for an alkane with 12 carbon atoms? So here are alkanes that you should memorize. CH4 is methane.
Mhm.
And these are straight chain alkanes. C2H6 is ethane. C3H8 is propane. C4H10 is decane. Excuse me, butane, not decane. I'm thinking about where I want to end up, which is decane. Okay, let's take a look at the formula so far. Do you see I'm increasing by carbon by 1 each time?
Yes.
What am I increasing the hydrogens by?
2.
Okay, so the next one's going to be C5, C6, C7, C8, C9, and C10, right?
Yeah.
And the hydrogens are going to be H12, H14, H16, H18, H20, and H22. Kind of made it like an assembly factory, didn't I? This one is called pentane. This one's called hexane. This one's called heptane, octane, nonane, and decane. decane, like a decade for 10 carbons. Nonane, like 9. Not known, kind of like 9. Oct for 8. Hept is 7. When you draw these, you can draw them as line drawings. And you can't draw ethane as a line drawing, and you can't draw methane as a line drawing. You can draw ethane as a line drawing, but can you see what that might be mistaken for?
Mhm.
So you say, okay, well, I'm going to draw it this way. Well, that might be mistaken for something else. Okay, so you're going to draw it that way. Oh, that might be an underline, or it might be a hyphen. Okay, I'm going to draw it that way. Ooh, that might be an L or an I. So no one really draws ethane as a line drawing. So I'm going to circle these and I'm going to go, nope. And methane, what are you going to do for methane? When you can't show any carbon-carbon bonds, you could do that, and that's mistaken for a period.
Yeah.
So nope, there is no line drawing for methane. There is no line drawing for ethane. But the rest of them look like this. So propane's a mountain, butane's a mountain and a half, pentane is 2 mountains or a bird, right? Seagull. Hexane is 2.5 mountains. Heptane is 3 mountains. Octanes is 3.5 mountains. And that's the way I draw them. When I do the zigzags, I just think, okay, I know how many these are, so I'm just going to do them in order like this. And this is going to be 4 mountains, right? And then 4.5 mountains. And you can actually count the carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you want to memorize these alkanes. Now, what is the molecular formula for an alkane with 12 carbons? Well, let's go back and look at these formulas. If we double this number, the number of carbons, how many hydrogens do we have to add to get to the correct number?
Well, I know that for alkanes, it's the amount of hydrogens is twice the amount of carbons plus 2.
Right, and can you see that in the formula?
Mhm.
If I double the 5 and add 2, I get 12. If I double the 4 and add 2, I get 10.
So our formula is C12H26.
So in general, it's CnH2n plus 2. And that's for any alkane. And it turns out it's also for branched alkanes.
Okay.
So these are straight chain alkanes. Versus branched. So let me show you a branched alkane. This is a branched alkane. Its formula is also CnH2n plus 2. How many carbons are here?
4,
So how many hydrogens based on this idea?
10.
And if we count them, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's only 9. Where's the 10th?
On that middle carbon.
On the middle carbon. So this formula works for branched alkanes and for straight chain alkanes. And both branched and straight are called saturated. They're called saturated because they have the maximum number of hydrogens bonded to the carbons as is possible. Now, unsaturated are usually considered to be alkenes and alkynes. Alkenes have a carbon-carbon double bond. Alkynes have a triple bond. And for alkenes, the formula is CnH2n. And for alkenes, it's CnH2n minus 2. Okay? Okay. All of that as an introduction for this really now simple problem. So CN H2N plus 2 gives us C12 H2 times 12 plus 2, which is C12 H26. So which of the following can be a cycloalkane? Now, cycloalkanes are not considered to be unsaturated, but for cycloalkanes, the formula is CnH2n, just like alkenes. So A is C3H5, and that doesn't work because it should be C3H6, right?
Yeah.
And B is C5H10, so that's okay. And here is the perfect example of a C5H10. I call it the house. This is another example of a C5H10. And this is another example of a C5H10. And this is another example of a C5H10. And this is another example of a C5H10. All of these are C5H10s. C, C14H30. That doesn't work. It should be C14H what?
28.
28. So this is an alkane, right?
Yeah.
And then we have C8H8.
Yeah.
It would have to be C8H16. So that one won't work either. Okay? Isooctane 2,2,4-trimethylpentane is one of the possible structural isomers of the formula C8H18. Draw the structure of this isomer. So we have to understand what this methyl means. So when we look at this name, 2,2,4-trimethylpentane, this name is short for 2-methyl, 4-methyl pentane. So that's what this is short for. We combine the 3 methyls together and say trimethyl, and we keep the numbers.
Okay.
This last part is what we call the parent. And this first part, these are called substituents.
Right.
Substituents are attached to the parent. So let's say that this is the parent right here. Here are the substituents you need to know. If you have a CH3, it's a methyl. If you have a CH2, CH3, it's an ethyl. If you have a CH2, CH2, CH3, it's a propyl. And I'm going to need another piece of paper here. So we're going to go with substituents again. We're going to go with substituents for 100, Alex.
What?
We're going to go with substituents for 100, Alex. Jeopardy.
Okay. That's what I thought you were getting at.
Okay, so here, CH3, and this is what it looks like when you have a line drawing. That's called a methyl. CH2CH3. This is what it looks like on a line drawing. That's called an ethyl. So can you see I have 2 carbons here?
Mm-hmm.
Can you see I have 1 carbon here? On this 1 carbon, how many hydrogens are attached?
3.
CH3, methyl. This would look like this, and it's called a propyl. And this, which looks like this, is called an isopropyl. Okay. And we'll not worry about any more of those, but there's a few others that you need to know. If you have this, which in a line drawing looks like this because you have to show the chlorine, it's called a chloro. What do you think this would be called?
Bromo.
Bromo.
Okay.
What would this be called?
Fluoro.
Fluoro. What would this be called?
Io.
What? Nope.
I don't know.
It's iodo.
Okay. So how are we getting the names from propyl and isopropyl?
Propyl. Hang on. Three carbons, propane.
Mm-hmm.
Okay, when it's not a straight chain alkane, but instead it's an attachment, you call it propyl. Propyl.
Okay.
Just like 2 carbons stand alone are ethane. When they're an attachment, they're ethyl. 1 carbon standalone is methane, but as an attachment, it's called an ill. So that's how we get these names. When you attach them, you take off the ane and you say ill. And when you say ill, that means, oh, it's a substituent.
Okay.
Okay. Now, if they're a halogen, you just take the name and take off ene and add O. Chlorine becomes chloro, bromine becomes bromo, fluorine, fluoro, and iodine, iodo. Okay.
Okay.
Now, there's a few others you might want to know, like if you had this would be called propane, cyclopropane. So as a substituent, what would that be called?
Cyclopropanol.
Cyclopropyl. So here, like methane, you take off the ane, you add ill. Here, you take off the ane, you add ill. Another one is this one, NO2. It's called nitro. Those are pretty much the ones I want you to know. We might learn a few more later. So let's go back to naming this guy. So we know the parent is pentane. So what do we want to do? We want to draw 5 carbons. So we'll double check. Is that 5 carbons?
Yeah.
Okay. Now we want to number the carbons. When you're drawing the name, drawing the structure from the name, I always number from left to right. Here's carbon 1, here's carbon 2, here's 3, here's 4, and here's 5. The numbers in front tell you where each substituent adds. So we have a 2-methyl. So do you see how when I draw that one line up there, it ends in 1 carbon? That one carbon is a substituent. It's a methyl. So that's a 2-methyl. Now I have another 2-methyl, so I need to add it here also.
Oh, not down.
No, I like to draw them this way.
Okay.
Because when you look at it, when you do this thing right here, this looks better than that.
Okay.
Because these look more evenly spaced than this, right?
Yeah.
Okay. Now for the 4-methyl, where are we going to put that?
On the 4th carbon.
There you go. And even if we did it this way, this would be also 2, 2, 4 trimethyl pentane.
Right.
And the reason this would still be the same is because we don't have to number the carbons from left to right. We number them, we find the longest line of carbons, and here it's 5. And you start numbering at the end that has more substituents closest to it. So here I've got 2 substituents closer to this end, 1 closer to this end. I'm going to start numbering at this end and number it backwards, so to speak.
Okay.
Okay, so this is one of the formulas with this. Draw and name the structures of 2 other in which the longest chain is 5 atoms. Okay, so here's the longest chain, 5 atoms, right?
Mm-hmm.
And I need to add 3 more carbons to this. Could I do this, and would it be different than that?
No.
The answer is yes. Because this would be 2, 2, 3 trimethyl pentane.
All right.
And ultimately, if the name is different, they're different things.
Right.
Now, is there another way I can draw this? And the answer is sure, you bet. What if I put 2 of them on the middle carbon and 1 of them over here? What would the name of this guy be?
2, 3, 3 trimethyl pentane.
Okay, now say it like you mean it.
I don't know if I mean it though. Is it right?
It's right, so say it like you mean it.
2, 3, 3 trimethyl pentane.
Okay, that's not quite there, but with practice, you'll get there. Here's what it sounds like when you say it like you mean it. Oh, it's 2, 3, 3 trimethyl pentane, obviously.
Okay.
And then if I had any hair, I'd flip it and go like that. Or give you the, what are you talking about? Of course, Willis, this is it. So there's 2 others. Are there any others? You bet. Name that one. This is a tough one. I'll give you a hint. It starts off with 3-ethyl.
Uh, 3-ethyl, 4,
2-methyl.
2-methyl.
1, 2, 3, 4, 5. See, if we number it left to right, it can be a 2-methyl instead of a 4, right?
Yeah.
We want the number to be as small as possible, so that means it's closest to the end, the beginning end.
So tell me about that 3-ethyl.
Well, take a look. How many carbons are here?
Well, there's 1 right there.
And how many there?
1.
How many is that total?
On, well, 2.
Those 2 carbons, that's 2 carbons, right?
Yes.
A standalone 2-carbon would be ethane, but it's not a standalone. So what is it?
Oh, ethyl.
Ethyl or ethyl, like Fred and Ethel.
Okay.
And on what carbon is that ethyl attached?
The third.
Okay. Now you might be wondering, why does the 3 go before the 2? And the answer is it's alphabetical based on the substituent name, not on its location.
Okay.
So ethyl would become before methyl. And if you had a propyl, it would come after methyl. Okay. And then there's one more. There's this one. See if you can name this one.
Is it 3-propyl?
Nope. 3-ethyl.
Oh.
3-methyl. So this is the ethyl and this is the methyl.
Okay.
To have a propyl, you have to have 3 carbons in a row, not 3 carbons like this.
Oh, not 3 total, but
3 in a row.
okay.
Okay, so that's the answer to that one. I believe this isooctane, this is the largest component in gasoline. Gasoline is a mixture, but I believe the majority of it is 2,2,4-trimethylpentane. Okay. Give the systematic name for the following alkane. So I'm going to redraw it. So this is me redrawing it, okay? And you want to faithfully reproduce it.
Okay. I wrote it down.
Okay. Now I'm going to redraw it again. Okay, what have I done here?
You did a line drawing.
It's not a line drawing.
Okay.
It's just a carbon drawing without the hydrogens, right?
Right.
I can turn this into a line drawing. That's not a problem, but I'm not going to do that. Okay, so the first thing we're going to do is we're going to find the parent, which is the longest carbon chain.
So hexane.
So 1, 2, 3, 4, 5, 6, 7.
Oh,
Heptane.
I didn't draw mine correctly. Oh, how come?
Now, let me show you something else before you get too weirded out by this. I'm going to show you another way to number it, okay? I'm going to start here. 1, 2, 3, 4, 5, 6, 7. So notice I can go up or I can go across for that next carbon. Now, if we look at this numbering up above, can you see that I have a substituent here on carbon 6? And I have a substituent here on carbon 3.
Yeah.
Can you see down here, I have a substituent on carbon 2 and a substituent on carbon 5.
Right.
Oh, I got to check something in the oven. Hang on a second.
Okay.
I burned the hell out of some chicken. I mean, it was
Aw,
it was black everywhere, like charcoal.
you didn't go get it?
I forgot. This was a few days ago. Okay, so which of these two numbering systems is the best? And the answer is this is the best because 2 plus 5 equals 7 and 3 plus 9, 6 equals 9, and you want the lower total.
Okay.
Okay, so we found the longest chain, it's 7, so that means heptane.
Mhm.
And then we want to locate and name the branches. Branch is another word for substituent.
Locate and name the branches.
Yeah, I call them branches. It's just easier than substituent.
Okay, so we did that.
So here, this is a substituent here on number 5, right?
Oh,
That's a 5-methyl, right?
I guess.
Well, how many carbons is it?
1.
So a 1 carbon is a methyl, 2 is ethyl, 3 is propyl.
Okay.
So here's another one. It's attached to carbon 2, so that's a 2-methyl, right?
Yeah.
And 3, you put it together. So when we put it together, we're going to say 2, 5 dimethyl heptane.
What about the other one on 5? Does that not count because it's part of the parent, right?
You mean this one down here?
Yeah, that's
Yeah,
not.
it's part of the parent, so it's already taken care of in the parent name.
Yeah, makes sense now that I said it out loud.
Okay. Now I'm going to show you another way to do this, and that is this. You can actually count them here. 1, 2, 3, 4, 5, 6, 7, right?
Yeah.
1, 2, 3, 4, 5, 6, 7. And here, 1, 2, 3, you got this methyl on 3. And 1, 2, 3, 4, 5, 6, you got this methyl on 6. And then I'm just counting to find the longest chain. I'm not saying it's actually number 1. I like to name things from line drawings better. So which end am I going to start from, this end or this end? I can tell that this is going to be part of the parent. And I can tell if I go up or down, it doesn't matter. So do I want to start at this end or this end? And I say, if I start at this end, the first substituent is on the 3rd carbon, right?
Yeah.
If I start at this end, the first substituent is on the 2nd carbon. So I'm going to start here.
So the lowest.
So that the first substituent is closest to the end.
Yeah.
And therefore it gets the lowest substituent number.
Right.
And so here, I think for me, it's easier to see that this is a 2, 5 dimethyl heptane. And why do I say dimethyl instead of just methyl?
There's 2 methyls.
There's 2 of them. That's it. Okay. Draw a structural isomer of the compound and give its name. Well, if we wanted to do it from this drawing, it'd be really simple. What we would do is just move this guy over 1. And it doesn't matter which way you move it. So if I do this, CH, CH2, CH2, and I move it over 1, I got to be careful because if I move it over to this carbon, I got to take a hydrogen off and call that CH2. And I got to put a 2 there. So you got to be careful when you're working with these guys. So what would the name of this guy be? 1, 2, 3, oops, 3, 4, 5, 6, 7, 8. This would be 3-methyl octane. And a real quick check of this is when you see this dimethyl, how many carbons are there due to the dimethyl?
2.
2 carbons. How many carbons due to the heptane?
7.
And that's 9 carbons, right?
Yeah.
How many carbons due to the methyl?
1.
How many due to the octane?
8.
And that's 9 carbons. So these are going to be isomers of one another because they have the same number of carbons and no double bonds or rings. You with me there?
Yeah.
Now, this is one way to do it. I think it's the harder way to do it. So this is what we had drawn before, right?
Yeah. Well,
And if we're going to do a structural isomer, why not just do the easiest one? How many carbons does it have?
10.
1 plus 8, 9, 2 plus 7, 9, 1, 2, 3, 4, 5, 6, 7, 8. Oh, yeah, this one has 10. I made the wrong drawing.
Oh,
My apologies.
I was wondering.
So I'm going to get rid of that. There, now it has 9 carbons.
Okay.
So wouldn't the easiest isomer to draw be this guy? 1, 2, 3, 4, 5, 6, 7, 8, 9.
Yeah.
And what's it called?
Heptane. Oh,
There's 9 of them and you have no idea?
no name?
There you go.
I forgot.
That was a great hint, wasn't it?
Yeah.
Okay. So what are some other isomers? Well, we could do this. That's 4 mountains, right?
Yeah.
So that's 3.5. I could do that. 2-methyl octane. I could move this over 1 and get 3-methyl octane. I can move it to 1 here and get 4-methyl octane. What would this be called?
3-methyl octane.
Nope, it's 4-methyl octane. 1, 2, 3, 4.
Oh, yeah. 1, 2. Okay.
Okay, so I've done all the methyl octanes I can, right?
I think so.
So then I'd do this. 7.
Right. That's an ethyl.
These are dimethyls.
Dimethyls.
Dimethyl. Methyl, methyl. Dimethyl.
Oh, okay. See, I was getting it mixed up with.
There are some ethyls, though. If you want to look at ethyls, they'd look like this. So here's 7. Here's an ethyl. Here's an
Okay.
ethyl.
That's right.
Those are the 2 heptane ethyls. Why don't I put the ethyl here?
Where?
Right there at number 1. And the answer is because that's a 3-methyl octane.
3.
Right. 1, 2, 3, 4, 5, 6, 7, 8.
Okay.
The parent is always the longest chain, not the one from left to right.
Mm-hmm.
Okay, so it gets a little tricky there. All right, so we've done this one. Now, this is a very informative problem because it's helping us to understand the names a little better.
Right.
So whenever you draw the compound, always start with the parent.
Okay.
So for A, I'm going to draw the bird because that's a pentane.
Right. And then we're going
And then I'm going to number from left to right. So 1, 2, 3. So where we would think of the body of the bird as being, that's carbon 3, right?
Yeah.
And I got to add an ethyl, which means 2 carbons. So here, that's 1 carbon when I draw one line. And when I draw one at an angle to that, that's 2 carbons. So that's A, 3-ethyl pentane.
Okay.
Now, of course, another way to do it is this way. Carbon, 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 carbon. There's my pentane. My 3-ethyl, carbon, carbon. And then I fill in the hydrogens. So that's another way to do it.
Okay.
Which way do you think I prefer?
The line.
The faster one.
Yeah.
Here's another way to do it. Pentane. Right? And here I'm going to come down with the ethyl part, right? And now I want 3 hydrogens on this guy. You with me?
Yeah.
So watch carefully. So what am I going to do with this guy? How many hydrogens do I want on the second carbon?
2.
How many hydrogens on the third carbon?
Just 1.
How many on the fourth?
2. I think.
How many on the last?
3.
How many on this first one that's attached?
2.
How many on the second one that's attached?
3.
So this is perfectly fine.
Okay.
Okay. For B, 2,2-dimethylpentane, what are we going to start with?
The bird.
The bird. Or you could start with the W.
Okay.
When you draw a methyl, that's a bond to 1 carbon, right?
Mm-hmm.
Okay, so where are we going to put these at? 2 and 3. So where is the best place to put them?
I put mine on the first peak and then the first and the dip in the middle.
In the first valley.
Mm-hmm.
That's it?
Okay.
Okay, C is 2,4-dimethylpentane.
Okay.
So you put them on the peaks, didn't you?
Yeah.
Or if you start with the W, you put them on the valleys.
Yeah.
And what this is these are little streams coming out of the valleys between the mountains. Isn't that lovely?
Mm-hmm.
D, 2,2-dimethylpentane. Did you put 2 peaks or 2 on the first peak?
Yeah.
That's it. Okay, so one of the reasons I teach you the line drawings is because when you get to organic chemistry, you want to be well aware of these line drawings. That's they use them a lot. They also use them in combination with condensed drawings and in combination with Lewis. So you need to be very well aware of the line drawings. Okay. 4 of 6 dimethyl hexanes are named below. Draw the structure of each and determine which isomer has a chiral center. Okay, so A is 2,2-dimethylhexane. So hexane means how many carbons?
6.
Okay, so here I've drawn 1, 2, 3, 4, 5, 6. So it's basically the bird with one more line, right?
Right. And then we're gonna draw 2 on the peak, on one peak.
That's what I would do, because that's just like 2,2-dimethyl pentane,
Yeah.
where we had 2 methyls on the first peak, but the parent was 1 carbon shorter.
Okay.
So you can see that for all of these, we're basically going to start with, since they're all hexanes, 2 mountains and a half, or the bird with a little extra, right?
Yeah.
Okay, now what's 2, 3 going to be?
Just one on the peak and then one on the valley.
First peak, first valley.
Yeah,
How about 2, 4?
both of the peaks.
1 on each peak. And how
Yeah.
about the 2, 5?
We just want, I guess, one on the first peak and then one at the very end.
Not the very end, the last valley. 1, 2, 3,
Oh, yeah.
4, 5.
Yeah,
If we put it on the very end, that would actually be carbon 6, wouldn't it?
that's where I was getting hung up at.
Okay. Now, do any of these have 4 different things attached?
Different? No.
First one, no, because this is CH3,
Right.
CH2, 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 CH3. But this carbon here, what about this one?
It has carbon, carbon, hydrogen. It's attached to a CH3, a CH2, and an H.
It's attached to a CH3, a CH3, a CH3, a CH2, 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 and a CH3, right?
Yeah.
Well, these are the same.
Right.
So, nope.
Right.
How about B? Does it have a chiral carbon?
Hmm. I don't think so.
It does. It's right here.
Oh,
Because when we look at what's attached to that carbon, isn't there a CH3 attached to it?
yeah. At the
Isn't
yeah,
there a hydrogen attached to it?
just one hydrogen, right?
Yes. Isn't there a CH2, CH2, CH3 attached to it? To the
Yeah.
left.
The
And then
rest.
to the left, isn't there a CH and then a CH3, CH3 attached to it like that?
That's to the left.
To the left.
Yeah.
Are those 4 different things?
Mm-hmm.
Even though this has 3 carbons and this has 3 carbons, they are not identical, so they're different.
Right.
So that's chiral. How about C? Are there any chiral carbons?
Well, yeah.
Which one? Which ones?
Wouldn't it be each of them on the peak?
No,
No?
this one is not chiral.
Okay.
Why is that one not chiral?
Oh, because 2 of the attached carbons are the same.
Yeah, they're both CH3s, right? Okay, so CH3 here, CH3 here, it's not chiral. What about
Right.
this one?
We have a CH3.
Okay, you have a CH3. What else do you have?
We have a CH2, CH3.
CH2, CH, and then CH3 and CH3, right?
Where do you get that one?
Right here, CH2,
Yeah.
CH, CH3, CH3. Oh, I think you meant this one, CH2, CH3 for this side.
Yeah, I was going to the right first.
Okay, I'm sorry. And then what else do we have attached?
Hydrogen.
4 different things. That one is chiral. What is the symbol often used for a chiral carbon?
Apparently it's an asterisk.
Apparently it's an asterisk. How about D?
No.
No. And is the asterisk above the carbon or below the carbon? And the answer is it's next to the carbon.
Okay.
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 Draw a structure for cycloheptane. Is the 7-membered ring planar? Explain your answer.
Planar.
Yeah, flat. Okay, so let's think about this. Cycloheptane. This is cyclopropane. That is the smallest ring you can have.
Mm-hmm.
And it is planar. This is cyclobutane. It is planar because the definition of a plane is 3 points in space, right?
Yeah.
Have you taken geometry?
In high school.
Okay, then 3 points defines a plane. How many points do you need for a line?
2.
2, okay? Now 4 points do not have to lie in the same plane, do they?
No.
Okay, cyclobutane is actually puckered. So let me give you an example of cyclobutane. So this is the square that would form from cyclobutane right here. And this is the way it's actually shaped. Where you see that's kind of folded.
Yeah.
You see that shape? Kind of puckered.
Mm-hmm.
Okay, so the 4 carbons don't lie in the same plane. This is the way cyclopentane looks. Now remember, each of these carbons is sp3 hybridized with 109.5 degrees, ideally, right?
Yeah.
Here, this is 60 degrees, which is way too tight. Here, this is about probably 92 degrees, a little bit better than 90, but not much. Puckering gets it a better bond angle. Here with cyclopentane, these are pretty much 109.5.
Okay.
So a lot of people call this an envelope look with the part that you fold over kind of folded up, not flat, not folded over, but at an angle.
Okay.
This is cyclohexane. And they call this the chair conformation because if you look at it, it almost looks like a lounge type chair or a sunning type chair, like a lawn chair. Here's the head of the lawn chair. Here's where you sit and here's where your legs go. Now, I've never really had to draw a cycloheptane, but if you had to draw a cycloheptane, it would look a lot like the lawn chair, except this. You'd have that.
Okay.
And here the angles are 109.5. What are the angles here? 109.5.
Right.
Now, why are these things not flat? And the answers are because if you had them be flat, the bond angles would not be the optimal, which would be 109.5 for sp3 hybridized carbons.
Okay.
So it's not planar because planar would not have 109.5 degree angles for the sp3 hybrid carbons. And that's basically it. And cyclooctane looks like this. To me, this looks like almost like a side table.
Yeah.
Where these are like metal bars and you put a wooden top on top.
Yeah.
But this is cyclooctane. Cyclooctane is not like this. So this is a stop sign. And that's flat.
Yeah.
Why is it not flat? These angles are too big. Okay. I think we'll stop after this one. So I kind of want to eat what I cooked.
What'd you make?
All I did was roasted some leg quarters. So they're going to be juicy and moist and perfect and not too hot. Among the 18 structural isomers for the formula C8H18 are 2 with 5 carbon chains having 1 ethyl and 1 methyl substituent group. Draw their structures and name these 2 isomers. So here, 5 carbon chain. So there we go.
All right.
1 ethyl and 1 methyl. So where are we going to put the ethyl?
I guess on 2.
Okay, let's do that. Now this is a 6 carbon chain.
Oh, it can't be on the end.
Well, it can't be on carbon number 2 because now we have a 1, 2, 3, 4, 5, 6.
Okay.
So you can't put it on carbon number 2. Where do you have to put it?
On 3.
Okay, let's put it on 3 and check your chains and make sure you don't have one that's longer than 5.
That works.
So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. This will work. So this is going to be a 2 ethyl, right?
Right.
Oh, excuse me, a 3 ethyl, not a 2 ethyl, a 3 ethyl.
3-ethyl.
Now we have a methyl. Where do you want to put the methyl?
It has to be on 3 as well.
Okay, you want to
Right.
put it there? So that's a 3-methyl.
I guess.
So what do we name this guy?
3-ethyl, 3-methyl pentane.
That's right. Now they say that there are two of these. What's the other one going to be? Well, the ethyl can only go one place, right?
Yeah.
Can the methyl go someplace else?
Yeah, on one of the peaks.
What would the name of this one be?
Do we name it the alphabetical branch first,
Yep.
even though it has a higher number?
Has nothing to do with the number. It's the lettering.
So 3-ethyl, 2-methyl pentane.
That's right. Now they say that there's two more, or two of these, right? Well, you said put the methyl on a peak. So I'm going to put it on this peak. What's the name of this one?
The same.
As what?
The previous one we just did.
Okay. Because we start numbering to get the substituents as close to the end, beginning end as possible, right?
Yes.
So these are the two. Now, do you see how doing these with line drawings just makes life so much easier?
Yeah.
If you don't quite see that, go back and try and do these problems that we've just done without line drawings. And you'll find that you can do them, but they will take longer. And so one of the reasons why line drawings were adopted is not only because they're quicker, but also because they're three-dimensional. So let me show you what I mean by three-dimensional. Do you remember how when we were putting things on this, I did this and you asked me, well, why not this? Do you remember that? So I'm going to show you why I did this. So do you see how that's the mountain?
Yeah.
Do you see how each of these carbons is sp3 hybridized and therefore tetrahedral?
Yeah.
Do these look tetrahedral on the end?
Yeah.
And so do these, right?
Uh-huh.
And that looks tetrahedral too, doesn't it?
Mhm.
Okay, so this one gets a little tricky, but we can basically do the same thing.
Right.
Here, I'm going to do this. And something similar for this too. So we can kind of see the three-dimensionality here. And if we had this guy here, I would have something that looked like this. And that doesn't look quite tetrahedral, does it? So this looks tetrahedral, and that's why I draw them both up or both down.
Right.
So it's to get the sense of the three-dimensionality of it. So line drawings are really, to most chemists, the three-dimensional drawing of something. So a lot of chemists, when we draw cyclohexane, we don't do this, we do this. So in a biology book, you might see this. And this might be like glucose.
Mhm.
But a chemist is always thinking, oh no, it really looks like this. It's not flat.
Right.
So, because it turns out that a lot of chemistry depends not only where the electrons want to go, but on how well things together fit. So for instance, you've shaken people's hands before, right?
Yeah.
Not lately, probably, but when you shake someone's hand, you use your right hand and they use their right hand, correct?
Mm-hmm.
And they fit together very well, don't they? But then there's always that odd person who, when you go to shake their hand, they stick out their left hand for some reason or other. Maybe their right hand, they have a cane in it. Maybe their right hand, it doesn't work as well due to some reason or other, so they shake with their left hand. Does your right hand fit their left hand as well? It doesn't fit, but your left hand would fit their left hand like a glove. It would feel weird because you're used to using your right, but the left would fit with the left very well.
Yeah.
Well, that's the way chiral molecules work. Chiral molecules have a left-handed and a right-handed shape. And these chiral molecules work with other chiral molecules in certain ways, so that in some cases they don't react, or in other cases they do. So there was this chemical that was used back in the 60s to help control morning sickness for pregnant women. And I always, when I tell the story, I can never remember the name, and I remember it later. But this particular chemical had a chiral atom in it. And this chemical was given to women to control morning sickness, which it did very well, but it also caused birth defects. And the birth defect it caused was that children would be born with shortened limbs.
Have you told this story before?
I tell it to every class I teach. So it turns out that one of the molecules was the one that controlled morning sickness. The other one caused the birth defect. The other chiral molecule caused the birth defect. And so naturally they stopped using this as a morning sickness cure immediately. So the chiral carbon, or the chiral molecule that caused the birth defect, caused it because it would stop growth. It would stop fast growing cells. And you know, when you have a baby, it starts out looking like a jelly bean, right?
Right.
And then it starts growing limbs, and the limbs grow really fast compared to the body. So the limbs were affected because they were fast growing. And so they naturally stopped using this right away, because the deal with the chiral molecules is that they have the same physical properties. So that means you can't separate them by boiling. You can't boil one and it boils off and then the other boils off. They all boil at the same temp. They have the same solubility in water. They have the same solubility in other solvents. So it's really, really hard to separate these things. They can be done, but it's really expensive and takes a long time. So it's not really doable. Nowadays, because organisms are chiral, they have organisms making chiral molecules so that you don't have any of the bad stuff, you only have the good.
Oh,
It's still kind of in its infancy. It's not, widespread, but basically you have these things doing that. An example of a chiral molecule is insulin.
Oh, so yeah, they're having bacteria.
So having bacteria, which make chiral molecules, make insulin, makes total sense.
Right.
And actually, it's better that bacteria make it than pigs, because normally back in the day, you get your insulin from pigs because the molecule they use was the same as the one we use. But you'd have to kill a lot of pigs for insulin.
Right.
So now they transplant it in bacteria and they harvest this shit, and it's really cheap for companies to make insulin.
Right.
And the sad part is they kind of sell it for a
Why-
enormous amount of money.
I was just gonna say that is really unfortunate that it still costs so much to get insulin,
Actually, it doesn't.
as much as it used to be, but yeah.
It doesn't cost as much in Canada or Mexico as it does here.
Well, this is America.
In America, we not only protect the right of companies to make things, but we protect their right to sell it at a high cost, even if they sell it in other countries less expensively.
Yeah.
So America really is kind of friendly to the corporate mind.
Mhm. Yeah.
But you know, they did figure out how to do it, and they should be able to make millions and billions of dollars off of it. Okay, maybe not. There's the whole social aspect to that you have to worry about.
Right.
So this particular molecule, it turns out they brought it back about 10, 15 years ago to do some more research on it, because someone came up with the idea that, well, if this attacks fast growing cells, maybe we can use this as a cancer therapy agent.
Yeah.
Because cancer cells are just cells growing out of control.
Mhm.
I haven't read any follow-up reports on it, but oftentimes you don't see too many articles on things that fail. You only see articles on things that work. So I'm imagining, since I haven't read a whole lot of articles since then, that it didn't really work that well.
Can you find out the name and tell me?
Yeah, eventually. It starts with a T, I think, but I just can't remember.
I can read on PubMed about these studies.
Yeah, all you have to do is go to Google and put a birth control chemical that caused birth defects 1960
Okay.
or 1970. But at any rate, they tried it. It turns out that it is kind of a helpful thing for a particular type of leprosy.
Really?
So they still make the drug. It's a treatment for leprosy with one caveat. And do you know what that caveat is?
Cost a lot?
No, you can't be pregnant.
Yeah.
That's the caveat. So men can use it without concern. Women who are not going to be pregnant can use it without concern.
Right.
And of course, with that particular type of leprosy.
Okay.
So that's why they talk about chiral carbons in this chapter, because it is important. And it turns out that organisms are built out of chiral carbons. Almost every molecule you have in you is chiral. Some simple ones are not, but the vast majority of organic ones are. Your DNA is chiral. Your proteins are chiral. So your fats are really not chiral, but proteins and DNA chiral. And so it turns out that if you got transported to the other chiral universe, you would eat food and not be able to digest it, and you would perish. Water would still work because water's not chiral, so water would taste like water. And that would be great. You could drink water for the rest of your, how long can you survive on water? 30 days?
I don't know.
So you could drink water for your last 30 days and that's it. You'd lose a lot of weight though.
Right. Well.
That'd be great for me. I need to lose about 60 pounds. All righty then. Good to work with you on these problems. Thank you for calling in. It gives me a chance to record these and post them for people to watch and keep at it.
Okay. See you
All right.
later.
Have a good day.